My bad, guys. So like I said, basically chapter 6, we're looking at all radical things. So today we're going to kind of focus on multiplying and dividing. You might be asking, well, why aren't we doing addition and subtraction? We'll be looking at that next. I guess this is just kind of the where the book goes, but basically we're going to be looking at in chapter 6. I mean, one big thing we're going to be looking at is just the operations with radicals, kind of how we handle that. But one thing you've probably, I mean, I've mentioned it before, or I've touched on a little bit. When you're multiplying radical expressions, basically you just multiply what's underneath your radical. It's basically, we kind of mentioned this a little bit when we talked about imaginary numbers. Like that's basically kind of how we simplify things with the negative root, basically separate the negative and the positive. But it's really just based on this idea. If you're multiplying radicals, you basically just multiply them and put them underneath the same radical. One thing I kind of mentioned, because in the delta math, they do have you simplify some radicals. One thing I do want to kind of specifically mention, like we've talked about index numbers, like a cube root has like a 3. If a square root really has an index number of 2. We just never rate that. So there is no root with an index number of 1. Because I mean, that really wouldn't make any sense. Because remember, what a square root tells you is basically come up with a number times itself that gives you what's underneath. It really doesn't make sense to find a number times itself once that would be the number. I mean, it basically wouldn't be. There would be no point of a radical, like a square root, like a radical with an index of 1. Like if you had an index of 1, like that would just be 5. Like, so it really wouldn't give you any value. So that's usually why you're never going to see that really. But basically the simplified radical form, there's 2 ways to think about this. One is, since these are square roots, you could try and think of perfect squares that divide into this, or you could just do a factor tree and just kind of brute force it. How delta math is going to show you a lot of times is basically you want to think of what's a perfect square that goes into 200. So you want to think of the biggest one if possible. But for example, I know 100 goes into 200. So you could rate this as, maybe I'll write it the other way. It doesn't really matter. But this would really be the square root of 100 times the square root of 2. So since I know the square root of 100 is 10, this would be the 10 square root of 2. This is how delta math will show you. But if not, you could always just do a factor tree. Like think of things that multiply. Like you could do 2 and 100. You could keep breaking it down and then circle any pairs. I mean, you could actually circle those if you wanted to. But even if you didn't, you'd get a pair of 5s and a pair of 2s. So that would be 5 times 2 is 10, and then you have a 2 left over. So I know it's kind of really sloppy and quick, but like I said, I don't.
Mr. Spoke, can you do it again? Because you went kind of fast.
Yeah, so if you want to do it with a factor tree, and sorry, I kind of wrote it sloppy, but basically you just think of any 2 numbers that multiply to 200. So I did 2 and 100. Oops, didn't mean to erase. And then just keep breaking it down. 100, you could do 10 and 10, for example. And then if you just you could actually circle that pair of 10s if you want. But let's say you didn't do that. You kept breaking it down further. You got a pair of 5s, and you got a pair of 2s. So when you have a pair, you pull one of those numbers to the outside. So 5 times 2 would be 10. And then since you have this 2 left over, that stays underneath your radical. So basically, what I just showed you here, there's 2 ways you could kind of go about this problem. I mean, one is just do like a basic factor tree. Don't think about it too much. But how they're going to show you in delta math is, if you look at the examples or the videos, usually they're going to tell you to try and pull out like a perfect square if it's a square root. If this was a cube root, you'd be looking for perfect cubes. I just want to kind of demonstrate there's more than one way to think about this. I personally don't care. Yeah, what's going on?
So you would pull out a 5 and a 2?
Yep, because you got pairs of those, so you pull out a 5 and a 2 to the outside, so you multiply those together to get 10. And then since you had 1, 2 kind of left by itself, or that wasn't part of a pair, that would stay underneath your radical. And I can try and show you better on one of these. Maybe so it's a little bit neater. So for example, the next question, I mean, let's say you wanted to just do a factor tree. I mean, you would think of anything that multiplies the 75. Yes. Aslan, I just saw your comment. Yep, that would be good. But so if you want to do like the factor tree, like I just noticed like 5 goes in the 75, so that would be 5 and what's 75? Oh, right, 5. I'm gonna brain for it. 75 divided by 5 is 15, and then that would be 5 and 3. So you got a pair of 5s, so that one of those goes to the outside, and then since you have a 3 left over, that stays underneath your root. So that's how you could do it as a factor tree. Another way you could think of this, though, is what perfect square goes in the 75. So I know 25 goes into that. So 25 times 3 actually would be 75. So that would be 5 radical 3 because the square root of 25 is 5. So 2 different, I mean, it's really the same thing, but if you can think of perfect squares or perfect units that go into a radical, you can kind of save yourself a bit of time. For 48, oops, I need to erase that. The biggest perfect square that goes into 48 that I can think of is 16 and 3, right? That would be 32, 48, yep. But I mean, it depends how good you are at seeing this. I think sometimes it's hard, especially when you're looking at like cube roots. Sometimes I think it's hard to think of perfect cubes or perfect, like if it's a 4th root, like perfect 4th powers that go into something. It's not always easy to see. I mean, for square roots, it's usually not too bad, at least for me. Everyone's a little bit different. But if you are, like, if you're just not seeing it, you can always just do like a factor tree. So any questions about simplifying radical? And keep in mind, if say this was a cube root, the only thing that would be different is you'd be circling groups of 3 instead of groups of 2 if you're doing like the factor tree method. If it was a 4th root, you'd be circling groups of 4, not groups of 2 or 3. So your index number basically just tells you how many you're going to circle at a time. If you're doing just like the factor tree method. But if it's a cube root, you're going to try and find a perfect cube that goes into these, for example. So let me know if you have any questions, but I just kind of want to reiterate this a little bit. Because I know in the one delta math section, there were some in that simplifying, I think it was called cubics. There was some that you probably needed to kind of either do a factor tree or a perfect cube method. But like I mentioned earlier in the notes, to multiply radicals, you can just multiply what's underneath your radical just to create a single radical. This only works if they have the same index, though. For example, in example 1, can you simplify the product of these rational expressions? For part A, you can't multiply or simplify these because they don't have the same index. Like 4th roots and 5th roots don't mix when you're multiplying. So same idea. If you have a square root and a cube root, you can't just multiply what's underneath. They would basically stay separate from each other. But if you do have the same index number, you simply can just multiply what's underneath. So since these are both 5th roots, you're still going to have a 5th root. Like you never mess with your index number when you're multiplying. You just multiply what's underneath. So this would be the 5th root of 10. And then usually the idea is once you get your new answer, you just see, can you simplify this? I mean, this one's really not going to simplify at all. There's nothing you can really do with a 5th root of 10. But just keep in mind, you can only do these if you have a like radical, or they have the same index number. For this next part, it says, if the radicand has a perfect root among its factors, you can use the product rule to simplify. This is called simplest radical form, not a calculated estimate. So these ones, the idea is they want you to try and pull out like a perfect number. But if you are struggling, you can always just do a factor tree and then just circle your groups of whatever you might need. But to kind of demonstrate for these different roots, so we have a cube root of 250. So you want to think of your perfect cubes. Like I said, I don't know if you know your perfect cubes that well, like 1 to the 3rd power is 1, 2 to the 3rd power is 8, 3 to the 3rd power is 27, 4 to the 3rd power is 64, 5 to the 3rd power is 125. And you could keep listing them if you want. But so I noticed that you always want to pick the biggest one if possible, but I noticed 125 goes into 250. So you could write this as the cube root of 125 times the cube root of 2. So that would just be 5 cube root of 2. If this is not your geometry slope, I just can't think of perfect cubes. I don't understand. Another way, like I said, you could do this question is just do a factor tree, like two things that multiply to 250. You could do 2 and 125. I mean, which would actually give you here. But let's say you didn't recognize that this is a perfect cube. You could do 25 and 4. It would be 5 and 5, 2 and 2. Since it's a cube root, you're looking for groups of 3, though. So you could make a group of 3 2s. So wait a minute. What did I do? 25 times 4 is not 125. Let me. Oopsies. Sorry, that should have just been 25 and 5. Big difference. So sorry, you can't make a group of 3 2s. You can make a group of 3 5s. So that would go to the outside. And then you have a 2 left over, so that stays underneath your cube root. But you see you get the same answer. So like I said, I really don't care how you do these. If you like just doing a factor sheet, that's cool. But if you understand how to kind of pull out a perfect cube or perfect number, it can kind of save you a bit of time. Part B, you have a fifth root. So it might be helpful to list your perfect fifth powers. Like 1 to the fifth power is 1, obviously. 2 to the fifth power, what's that? I don't really know my perfect fifths. That's 32, right? Yep. 3 to the fifth power is 243. So it's obviously way too big. So 32 goes into 160, right? Yeah, 32 and 5 would work. So this would just be 2 fifth root of 5. So
Mr. Swope, I'm confused.
basically, based on what your root is, you want to here's how I'm approaching it is, since this is a fifth root, like 1 to the fifth power is 1, 2 to the fifth power is 32, and then 3 to the fifth power is 243. So I don't have to list anymore because they're getting too big. So you want to check which one of these perfect fifths divide into your original number. So since 32 divides into 160, you could rewrite this as the fifth root of 32 times the fifth root of 5. And then since the fifth root of 32 is just 2, you can just kind of simplify it. I don't know if that makes sense, but how about you guys try part C and part D? But like if it, to kind of help you with C, like since it's a fourth root, if you list your perfect fourths, like 1 to the fourth power is 1, 2 to the fourth power would be 16, 3 to the fourth power would be 81. They get too big after that. So you should see 81 goes into 162. So you could see if you could simplify it from there. But let me know how this part's going, if this is making any sense. But this is how delta math is going to show you, like anytime it simplifies a radical, like with the number part, it's usually going to do it kind of like how I'm showing here. So I'm going to go over these two. Like I said, it's hard to kind of gauge since I can't see you. I hope I'm not jumping too far. So I do apologize if it's ever frustrating. So, yeah. So for this one, since I know the fourth root of 81 times the fourth root of 2, like that's the same thing as the fourth root of 162. Since this is like the fourth root of 81 is 3. So this would just be 3 fourth root of 2 because you can't simplify that piece there. D, we have a cube root. I don't know. Like I said, the more you do these two, you kind of remember your perfect numbers, like especially if you're dealing with them a lot. So you probably don't have to list them out, but like your perfect cubes, like are 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So like, I mean, you never got to go bigger than what you start with. So, and you always want to do the biggest one if possible. 27 doesn't go into 56, unfortunately. So 8 does though. So this would be the cube root of 8 times the cube root of 8 times 7. So this would just simplify to be 2, and then you can't simplify the cube root of 7. So there are other ways to do these problems, but like I said, this is kind of like, I don't know, maybe I call it the sophisticated approach. Like this is what you're going to see in a textbook. This is what you're probably going to see. This is what you're going to see like on the Delta Math videos or examples. You might see this is probably like if you're in a college level class, this is probably how they would work it out. They're probably not going to do a factor tree because in theory this is faster. But sometimes when you deal with really big numbers, I don't know. Sometimes I find myself just doing a factor tree because it's not always easy to find what perfect cube, or especially if you're dealing with bigger index numbers like a perfect fifth that goes into like 2,332. I don't know. Like, so sometimes it's just like I don't know. It depends on your philosophy. Another thing we kind of mentioned last week was how to deal with variables. Basically, if most of the problems on the notes from the 3-1 we saw, it worked out perfect. But remember, you basically take your power divided by your index number. Like a to the 20 would really be a to the 4th. Not a to the 4th, sorry, a to the 5th, because 20 divided by 4. Remember, the reason why is this, I don't know if I'm going to, I'll write it out, I guess. But this is really 20 a's. 8. But 20 A's could really be broken up into 5 groups of 4. So basically, when you circle these groups of 4, one from each one of these groups comes to the outside. So you really pull out 5 A's. But that's why it's working, if that makes sense. But basically, you just take your power divided by the index number. But just to kind of keep in mind, sometimes if it doesn't work evenly, like if you have a 14th power with an index of 4, how many groups of 4 can you make out of 14? Well, if you just count on your fingers, 4, 8, 12, you can make 3 groups. So you're going to have 3 A's on the outside, but that would only be 12 A's for a 12. So you have 2 left over. So those stay underneath your radical. And it's similar with numbers. Like if you think about 14, that one doesn't really make any sense. Where are they going with this problem? There's really not anything you can do with 4 radical 14. I wonder if that's a typo. Yeah, I'm guessing this is a
radical.
Because 4 radical 14, you can't simplify it. Like you can't make any pairs out of 14. So I think that might be a mistake. Or
Mr. Smoke.
Yeah.
That's not a radical. That's a division thing.
Oh, that is a division sign. That looks funky. Oh, okay, that's the idea. Okay. Oh, they're just basically showing you what I just did there. Oh, that makes so much more sense. Okay. Because that's kind of the logic. Like 4, that would be 2, or sorry, that would be 3. Well, so then you would have a remainder of 2. But that's basically what I did here. If that makes sense. Got it. I was thinking that was a radical, though. I was like, that doesn't make sense. That makes so much. That's what they're going for. My bad. So these other examples, like I said, if you basically take your index number, divide it into your variables. So a cubed divided by 3, that would just be 1 group of 3 A's. How many groups of 3 can you make out of 8? Well, that would be 2, but you would have 2 left over. Because like 2 groups of 3 would be 6. Then you have 2 B's that weren't in those groups. Keep in mind, like I said, if it's a square root, remember your index number is a 2. So you'd be cutting how many groups of 2 can you make? Well, that would be, you can make 3 groups from 7, but then you have 1 left over. So that stays underneath. For the 9y's, you can make 4 groups of 2, but you have 1 left over. And then for z, you can't make any groups of 2 out of 1z, so that just stays underneath. For part C, if you're, remember, that's just 1x, so you can't make 5, a group of 5 out of 1, so that x stays underneath. For the y, you can make 1 group of 5, but then you would have 4 underneath still. Any questions about these? I mean, this was kind of hit on in some of the Delta Math sections, so this should be kind of review from what we've seen. but let me know if anyone, if you are having questions. But basically, you just take your power divided by the index number. If you have a remainder or whatever you have left over, basically stays underneath your radical sign. Okay. So kind of putting together what we've talked about, I feel like it's been a little bit jumping around, but basically when you're multiplying radicals, you're just going to multiply what's underneath. And then you're going to use these different ways we've talked about simplifying to simplify your product. So for a problem like A, you would just multiply what's underneath the radical. And then you just want to see, can you simplify the square root of 12? Don't leave your answer like these. Or is it the number? Brooklyn, were you talking about the previous questions or are you talking about this section here? I just want to make sure I'm not. So let me know. The previous. So you said, are these being multiplied by it or is the number on the radical? You're always looking at your number on the radical. That's called your index number. That's what you'll be dividing. So you said for like the today example. So like, I mean, basically how you want to like think of a question like this today one is, since you have a fourth root, basically you're making groups of 4. So how many groups of 4 can you make out of 14? So I like to just count on my fingers. So 4, 8, 12. So I can make 3 groups. So that's why I have a to the third on the outside. But 12, there's still 2 left over of the 14. So that those 2 stay underneath. I don't know if that answers your question exactly or not, but let me know. Basically you have like 4, 8, 12. So that's like 3 pulled to the outside, but then the 2 left over that aren't part of a group go under, stay underneath. Oh, yes. Great catch. My bad. And this is something I am guilty of doing. One thing in these problems, yeah, your index number shouldn't change. Yes, so that is one thing I am guilty of. I don't think I did it in any of the other problems, but yes, your index number should never change with these. Yes, and I am guilty of that. That's an easy mistake to make, but I mean, and I'm guilty of it myself. But that is something you really do want to be careful with. Yes, good catch. My bad. Now I get what you're saying. But back to this question. That makes so much sense now. So you could do, like I said, if you want to do a factor tree or if you want to like pull out a perfect square. If you did the perfect square method, you could pull out a 4. So that would just be 2 square root of 3, or you could just do like a quick factor tree. So however you want to simplify it, like I said, find what works best for you. But I'm going to kind of demonstrate probably how you'll see it in Delta Math, just so maybe there's some unity between the different materials we're using. For B, you would just multiply what's underneath. So some of our exponent rules are going to come into play. Remember, when you're multiplying exponents, you add the powers. So for the x's, you'd really have 7 x's. For the y's, you'd really have 4, because keep in mind, this is really y to the first. And then you want to kind of use what we did in that last section. How many, you're making groups of 4. So you can make one group of 4 from the x's. You can make one group of 4 from the y's, but don't forget what you had left over. So from the 7 x's, you would have had 3 left over. From the y's, you wouldn't have had anything left over. So this would just be x times y, 4th root of x cubed, which I know kind of looks messy, but that's all you can do with this question with the variables. So kind of putting this together, and I know I'm just doing a bunch. I don't know if this is helpful, if maybe I should just give you some time to try some, but tomorrow we'll be doing an assignment, so you'll definitely have time. But like I said, just multiply what you have underneath and just simplify it based on how we've seen. When you have a coefficient and a variable, basically do your number part on its own and then just do the variable part. So for 720, ooh, this is a big number. This is why I said like sometimes like the perfect square, it's not always easy, at least in my opinion. what's the biggest perfect square that goes in the 720? I wonder if, I don't know if you see this, but I was thinking maybe 144 went into it. I mean, it was kind of a lucky guess, at least for me. But you could actually write this as the square root of 144 times 5. So this is a question, like I said, I don't know if this would be something easy to see. I mean, you could always just kind of plug and chug some perfect squares to see if they divide in. But a question like this, you might want to do a factor tree. It's your call though, but this would be 12 square root of 5. But then for our variable parts here, I'm going to leave myself some space. But then if you do your variable part, remember with the square root, it's the index number of 2. So how many groups of 2 can you make out of 4? Well, that would be 2 groups of x's. So none, we used all of them too, so none stay under. For 5 y's, we could pull out 2 y's, like 2 and 4, like 2 groups of 2. But then there is still a y left over. So this would be our answer, if that makes sense. But basically, if you have a number part and a variable part, just kind of do your number part on its own, do your variable parts kind of on their own, and then just kind of put them together. But how about you guys try D? Honestly, and there's different philosophies too. Some people multiply it out. Some people would even keep these separate. Like some people will multiply it out. Some people might just, especially if you like to do the factor tree, they might keep these separate from each other. I mean, it's kind of a personal preference. I usually just multiply it out, but sometimes it's easier if you actually keep it separate. So you could do a factor tree. If it helps, what's the big perfect square that goes into this? It's 225. Go into it. If it helps to kind of get your number part, you could simplify this as being 225 times the square root of 7. But especially when you get, like I said, when you get big numbers like this, it can be a little bit hard. I mean, I've been seeing them myself, but I know like if I was in like a high school student, my number sense probably wasn't always the best. So I don't know if I'm sure some of you guys in here are seeing it, no problem. But I'm sure some of you guys pulling out a perfect square of like a big number like 1575 can be a little bit tough. So if you might want to do if you can't see this, you could always do a factor tree. And one tip is you can always start with like these as your first 2 factors and then just kind of break it up from there and then look for pairs. So we're running a little bit low on time. So we probably will have to finish. We'll probably have to look at the dividing part maybe tomorrow. I don't want to really just brush it, kind of cram it in. But we'll see. Division's basically the same idea. Basically, you're going to divide what you have in your 2 radicals and then see what you can simplify with it. So, I mean, even though you might be like, oh, division, it's really not too different. But then we will talk about rationalizing the denominator. That can be kind of an annoying thing, but it's something you'll definitely come across probably in future classes. So since we're just running a little bit tight on time, if you did simplify this, 225 is the square root of 225 is 15. Oops. So this would be 15 square root of 7. I like to leave some space for the variable part. Since this is a square root, how many groups of 2 can you make out of 6? Well, that would be 3 groups, and then there's none left over. For 7 y's, you could also make 3 groups, but you would have 1 left over. So that stays underneath the radical. So this would be your answer. So usually multiplication is not too bad, but the one problem is when you're multiplying your numbers underneath, sometimes you get pretty big numbers like 1575. Like that can be hard to kind of simplify. in radical form. So, but one piece of advice, if you're trying to do this, pulling out a perfect square, just try and divide things into 1575, especially with squares. You probably know a lot of perfect squares, but just try divide. I mean, it's a bigger number, so I would start with maybe 10 square, like start dividing by 100, start dividing by 121, start dividing by 144, start dividing by what is it, 169. What's 14 squared? That was 196, 220. Like, if you know your perfect squares, just start dividing them until you get one that works. But I mean, once you start seeing it, and since it ended in a 5, I knew I'd have to have something with a 5 here. Like, that's one tip if you know things about like division rules. Those can help a little bit as well. So let me see. Got a little bit of time, but honestly, we should do at least one of these so we can see if you got numbers in front. But we'll cut it off here at quotients. We'll do these quotient notes tomorrow, and then I'll kind of give you the rest of tomorrow to kind of work on it in assignment. I'll try and get it up today, though, so if you want to start at least the multiplying parts, you can. But I'm just going to do one more example because we're a little bit short on time. But they all look relatively reasonable. I mean, obviously, G's got just more pieces. But for a question like E, just keep in mind, if you have like a number in front of your radical, you basically multiply the outside numbers together, then you multiply the inside numbers together. So this would be 27 square root of 14xy. And then you just want to simplify it. So the x and the y, you can't pull any x's out because you can't make any pairs. But for the 14, that also doesn't simplify, because you can't like make any, there's no perfect squares that go into 4, like 14 is just 2 and 7, so you can't make pairs of anything. So this would actually be your answer for this question. You should always check, can you simplify this? But there's actually nothing you can do with the square root of 14xy. You can't pull pairs of anything out. So, and that'll happen. Sometimes you really can't, it might look like you're going to be able to do a lot more, but you really just end up can't being able to do much. So maybe I'll just do F because maybe E wasn't very satisfying. But this would be 12 square root of 16x squared. So now you can simplify this. Like, I mean, the square root of 16, hopefully you recognize that. That would just be 4. So 12 times 4 would be 48. And then the square root of x squared would just be x. You basically have nothing left over. So if you don't have anything left over, you're just not going to have a radical. So that's pretty much all I've got for today. I did record these notes. I'm sure it was a little bit rough.